Okay, so I'm going to pretty much continue from where we left off yesterday. So we were looking at basically graph mining problem in a distributed setting. And we were looking at, what are the available sort of paradigms. So one approach, as we discussed last time, is that you can code up your own algorithm, right? So obviously, given a cluster, you can use message passing, and you can do everything on your own. Or you can obviously try to leverage the distributed framework that we have, MapReduce, Hadoop type of systems. And in the case of graphs, we have Giraffe and GraphX and all these packages. And the advantage, of course, is that you don't have to think about actually programming the whole distributed system, because the implementation of these packages, meaning the Giraffe type of system, is that it will basically leverage all the machines at the same time. So essentially, you take your data, you upload the data into the distributed file system. Underlying this is the Hadoop distributed file system, HDFS. And HDFS basically, it basically ensures that things are, there's a redundancy built into the system, so it will replicate your data 3 times, and then it uses computation nodes and name nodes to basically look up the relevant piece of information. So as I said, that's all on the systems front. And there's a lot of work that has to be done to implement these things correctly and in a scalable manner. But our main goal is to sort of leverage these types of platforms for graph mining computation. So that's one thing. So we're going to use, let's say, Giraffe or GraphX. And the other thing to note about these systems is that they basically operate on, so if you think of the MapReduce type of a paradigm, and many other graph computational problems that you can implement on top of these platforms, they use this BSP programming paradigm, which is called the bulk synchronous programming. So this is basically pretty much, you can think of this as, everyone does a whole bunch of computation, okay, and then you sort of synchronize. And then you do another sort of phase of computation, then you again synchronize another phase. So it's pretty much distribute, pretty much put a barrier or a synchronization among the nodes so that you can tally the results. Right? So depending on the computation, how many iterations you have to go through depends on the task that you're trying to do. So in graph mining, when you're trying to find these frequent subgraphs, each BSP step or super step, whatever the term you might use, is basically, it might be a level of the computation. So I'm going to do all single edges. Everyone will count all the single edges in the system. Then you synchronize, and the synchronize basically also does the reduction. So you basically reduce, you sum up all the frequencies, and then after that you can basically figure out which are the frequent patterns, meaning the frequent single edges, and then you again say everyone will extend these edges in the next phase. They will again synchronize, reduce and synchronize, and this way I'll get all the 2 edge, the 3 edge, and so on. So it's pretty much natural to map that kind of problem onto the graph situation, but this thing works pretty much in the sense that so that's this is how you would implement this in a MapReduce type of a framework, right? So if I give you a graph data set and you use MapReduce directly, you'll do this. Now, this other paradigm that is very popular is a thing like the vertex, because many of the graph computational problems that you've seen, page rank, shortest paths, they are actually very easy to implement using the thing like a vertex paradigm. So I'm going to today try to go over these 3 different paradigms. There is think like a pattern, think like a vertex, and the third thing will be think like an embedding, which is what I'll spend the most time on. So let's start with this think like a vertex, because this, as I said, is extremely useful and very powerful approach for mining really, really large graphs because you get pretty much almost perfect load balancing here, because you can take the entire graph, okay, and the graph can have billions of nodes, and so the idea is that okay, so you've got a very large graph. So given a very large graph, what you want to do is, let's say I want to compute some, so the idea is that it's a vertex-centric approach. So given a very large graph, I can simply partition the nodes, essentially, among my compute nodes. So I may have, let's say, P is equal to 1,000, so let's say I have 1,000 machines or computers, whatever distributed system. And so the idea now is that, and this graph has a billion nodes, right? So every node essentially can be assigned to one compute node, so one machine. So this will get, so let's say, let's make the life simple, let's not have 1,000, let's just say we have 3. So, and this graph has many more vertices. So I can do a random assignment or whatever the system decides, basically. We don't control the placement of the node on the machine. The system will take care of, pretty much distributing this work, because there is, of course, some it may use hashing, it may use other, mechanisms under the hood. So whatever it is, we don't really care. This might get assigned to process number 1, to machine number 1, to machine number 2, to 2, to 3, to 1, to 2, 3, 2, whatever. So the point is that, you completely distribute the graph. Every node is assigned to one machine. And now the distributed system, right, can essentially, every node can be pretty much operated independently. So if, at any given point in time, in one super step, remember the idea was that you collect all the inputs from all your neighbors, and then you push whatever, you do some local computation on those, and then you push that information out to someone else. So it's pretty much an iterative graph update type of a problem. So vertex, if you think of from the point of view of machine number 1, these 3 nodes are assigned to that machine. So it will basically look at this node, say, okay, who are the neighbors? So it just has to know the old value for the neighbors, okay, whatever the previous value was. So it will say, okay, borrow the value from here to here. There's only one edge. This guy will borrow values from here, values from here, values from here. So in the same step, all this is happening. So simultaneously, in parallel or in a distributed manner, everyone gets the input, they compute something, and they push the information out. That's one step. And now you keep on repeating these steps, right? So this is the basic idea. And you can see that this is a very nice way, because pretty much all the resources will be utilized. And a very large graph, everything will be more or less balanced, as long as you do a good job assigning nodes to the machines. So there's a graph node and there are machines. So the G itself is pretty large. The vertex size is n, and you have P processors, and so you can simply equally divide them, n over P. That's the amount of work per machine. So in this paradigm, yesterday I had this, and this is fine. So let's look at this one first. So for example, shortest paths are very easy. So this is actually an example of a single source shortest path. How you would do this on a Pregel-like or a giraffe-like platform. So here basically what's happening is we want to do the single source. So yesterday I didn't really realize that, but we are saying that 0 is your source node, okay? And you can only do vertex-centric computations. So what happens in the first step? So this is a super step. I don't know if you can see it in the back. Maybe it's a little bit small. But the edge structure is given here. So basically everyone initializes the shortest path to infinity. Right? So I want to know the shortest path from 0 to everyone else. So initially everyone else, I get a value of 0 because I'm starting from that from that vertex, but everyone else gets a value of infinity. So in one step, the only thing this node can do is communicate with its neighbor, basically. Look at the edges. And so it says, okay, and by the way, this is a weighted shortest path. It's not just a simple number of edges, it's also the weight on the edge. Okay? So you see the connectivity here, this edge is a bidirectional edge, and the weight is 4. This edge here is, it's a unidirectional. It goes from this node to this node, but the weight on this is 2. This edge has a weight of 1. This is a bidirectional edge and it has a weight of 2. So we have a weighted graph, and you want to find shortest path from this vertex to everyone else. What is the total weight, the minimum weight? So in the first step, like I said, all you can do is you know that the neighbor, this vertex is a neighbor, and this vertex is a neighbor. So it will basically push that value to those guys. Okay? And so that will be the output here. So you basically get, you take the 0 plus 2, you get the 2 value here. You take the 0 plus 4, and you get the 4 here. And that's basically the end of the initial step. So this is showing you, so forget about this for a minute. This is basically, in this step, you just take this and you push that value 2 here, you push that value 4 here. And now we go to step number 1. Okay, now I repeat it. So now the state looks like this. Okay, so what you do next is, each one of these guys, okay, so like 2 will now push its information, and then 4 will push its information. Yeah. Yeah, but the point here is that we're doing single source.
Yeah, but still everything is exchanging. Because it's in parallel.
Okay, but these guys cannot do anything because
they are getting infinity, but they are getting the minimum of infinity.
I guess they could do it. You could do it, or you could just say that if my weight is infinity, I'm not going to activate. So in other words, in the previous approach, you say a node gets fired up only once all the neighbors have values less than infinity, because otherwise there's no point doing it, perhaps. So let's see. So anyway, I think that's a good point. They could either look at it and say no change, it will still be infinity. That way everyone will be busy doing something. Or you might say that the computation in this case, it basically goes in basically waves. It will be the frontier. So it's kind of like a breadth first expansion from your starting vertex. And so the all the vertices at a certain depth will get activated at some point in time. So this would depend on how you implement it, I think. This would be the actual, the code that you would implement. So it could be everyone does the whole thing, or they just look at it. But I guess that makes sense. You can definitely update everything. So this guy will look at that and still infinity. So I think it's okay if we assume that that's our paradigm. So let's everyone does some update. Okay. So now this guy. So now the situation looks like this. And so let's not look at this anymore. So here you have 2 here. And so this edge will be, so now this node, since it's connected to that one, it will look at its neighbor and say, take my current value, and add the 1, because this edge has weight 1, right? And then update that. If it's less than if it's less than 4, then you need to update that value. And then this 2 will also update this one. It will say push this 2 here, but the weight of this edge is 2. 2 plus 2 would be 4. So that's what you get basically. So you push this here, and you get this value 2 plus the weight of the edge. You get the weight of 4. This 2 with the neighbor is 1. The weight of 1. So you get a 3. And then, of course, 4 is also doing something. 4 is pretty much a neighbor of 0, but then there's no change. It's 0. It's still 4. 0 plus the 0 plus 4 will still be 4. So, but and then you have to compute the minimum. So I guess the point is that you look at all the incoming things, and you look for the smallest. So among all the updates that can happen. So there is an update from. There's an update from 2, and from the 0 we already did actually, I'm sorry. So from the 0 probably you don't have to do it again. and then you basically see if anything else remains. And at this point, all edges have been seen, all the weights have been updated, so there are no new messages, and this is your final output. So, but this is each of this sort of is one step. So in the bulk synchronous programming, every sort of update, a global update across all the systems, that's one update. And so this is the final set of shortest paths. So starting from 0, your distance to yourself is 0 to this is 2, 3, and 4. So you can see that this kind of computation is very easy to. So in terms of the actual implementation that someone like me or what someone was programming, they would just have to write the logic at this vortex. So what happens when you see incoming, pull in incoming information, add the look at your neighbors, look at the weight, add the weight of the edge, and then compute the minimum. That's the only computation you have to do. So it makes it extremely easy to think about very large scale problems in a very scalable manner.
Excuse me, sir.
Yeah.
Sir, in this, what we are assuming that the complete graph is on every machine.
No, because here actually you just need to know the neighbors, right? I mean, so it's a good question because the point is that when you, so let's go back to this figure here, right? So assume you're doing this on this graph. So, of course, if I assign this node to a machine and this node to a machine and that node to a machine, you need to be able to query. You need to be able to ask, who are my neighbors? Okay? Now, since we are not really controlling how the graph is, which node gets mapped to which machine, that means the underlying file system where you store the graph, that has to basically satisfy your query. So what they normally do, so this is how it actually works. Initially everything is on disk. Okay, so there's nothing in the main memory. So you don't assign anything to anyone. Now the work gets assigned. So this guy gets on machine 1, right? Now the first time the one asks the query, you'd actually issue a query to the distributed file system, you'd fetch the information, and then you'll do a local cache. Okay, you'll keep it in the memory at that point. So then again, this node will query something, it will ask for the neighbors, and again, you keep it in the memory. Every time you ask a query, you keep a cache local. So that in the next phase, you already have everything that you need in your local memory. So this is how the data gets pulled from the different machines. But this is a good point because this is exactly the kind of issue when you talk about minimizing the communication in the system, that ultimately you have to worry about where the graph is. Did you actually partition the graph? And the graph partitioning and your computational partitioning may not match each other, right? So all those are very valid questions. But at least at the at the level at which we are talking, we're not going to bother about that. I mean, when I say not going to bother about it, that if you just want to use the system, you just say, I'll let the system worry about doing all the caching, this and this. I'll just focus on writing the logic of this. So in other words, it makes it very easy to write your code. It need not be the most efficient solution, but then you also do not spend that much time, right? You still get a reasonably scalable solution, or you can actually start doing things. Now you say, I did this and it took me a day to do it, on a, let's say, Facebook type of a network. Then your next thing would be, how can I optimize it? Maybe do it in 1 hour or in 1 minute, whatever. So then you have to say, okay, no, I'm not going to rely on the default parameters. I'm going to actually partition my graph in certain ways and so on. So those are all very valid questions. But right now you just think conceptually this is what you need to do. And there's a lot of system level work you might want to do to actually improve Giraffe or improve the other platforms. Okay, so that was the shortest path. And of course PageRank is pretty much the same. PageRank is in fact easier, because all you have to do, like we said last time, is that you're doing a matrix vector multiplication. The matrix is simply, as the, so in the PageRank we know that we just look at the incoming ranks, right? So you borrow the ranks from other nodes, and you pretty much just sum them up. So here you're just doing a summation operation. Sum up all the ranks, or the U values. let's call it the page rank. I think R is fine. So it's R1, R2, R3. So you pretty much take all the incoming edges, sum them up, and then you send the, so the computation that's happening at every node is look at your neighbors, look at the rank of your neighbors, add them up, which is what we did, and then any outgoing edge, pretty much, divide by your out degree. And then just ship that information out. So that's all. So you just have to write a simple piece of code. And this is just maybe two lines of code, right? For all neighbors of U, add a sum, and then, for all outgoing neighbors, push this value divided by the degree of the sum. That's it, 3 lines of code. So it's extremely easy to program very large systems. So remember, you didn't have to worry about fault tolerance, you didn't have to worry about sending messages back and forth. 3 lines of code basically gets you a scalable algorithm for doing page rank. Okay, so this is all very good, and in fact many graph computations can be put in this framework, and so that's why it's an extremely powerful paradigm for programming and doing graph computations. Now the question is, of course, we want to do graph pattern mining. So structural stuff we can do, eigenvalue stuff we can do, right? This is pretty much eigenvalue problem. So that means I can take a Laplacian and I can do computations of eigenvalues. Now, if you want to do clustering, and we saw, for example, things like the Laplacian and computing the eigenvalues of the Laplacian. Now, this is good for computing one dominant eigenvector, right? So here I'm just saying there's one value, and I'm going to, there's one vector essentially in the page rank, and the page rank vector was pretty much the eigenvector, the dominant eigenvector for the Markov matrix, right? So you basically, for page rank, you basically start from A. From that you compute your Markov matrix, and then you add some random component to it, and this is your final matrix M. And then you compute the eigenvector for M transpose. So you say basically eigen M transpose. So this is essentially what you're doing. And this eigen M transpose, this dominant eigenvector computation is essentially this notion of, you can compute by looking at all the values coming in and then pushing the values out. So every vector is computing, so you're computing the final, so this is the, actually I should just say dominant eigenvector. So we compute U, which is the dominant eigenvector of M. And so this is actually the U, so if this is vertex I, this is the UI entry. So this whole vector U has many things. So you pick the ith entry, and the ith entry can be computed exactly in this manner, because this is essentially a sparse, we call this a sparse matrix vector multiplication problem. So this M, because as we saw last time, the page rank vector is basically M transpose to the power K. So you keep on taking the iterative approximations to that. So ultimately, upon convergence, this would become you start from some U naught, start from some starting point and keep on taking power of the matrix. So repeatedly, all you're doing is you're updating this, you're just updating this vector, right? So actually, I didn't even have to write this is the final result, but actually, the main computation is that UI plus 1, okay, I'm now misusing my hand. So you start, so U is basically M transpose U. You just have to keep on repeatedly updating this. So just multiply on the left by the matrix. So start from some initial vector U and keep on multiplying, keep on multiplying, keep on multiplying. Eventually you will converge to the final vector. And that multiplication is exactly this, because every row of M, right, so this M transpose, that's your row of M transpose, and this is the vector U. So you're basically borrowing the sort of the flow from all the, so every row will multiply and update this value here. So, essentially that boils down to this computation here, that's the one that we talked about. So page rank is fine. Now if you want to do clustering, you have to compute maybe, if I want to find 3 clusters, to compute 3 eigenvalues, 3 eigenvectors. So what we have to do then is we have to expand this to actually a vector of size 3, because now I need to have 3 different eigenvectors that I'm computing, right? So there's a lot more that has to be done. So it's not clear, it's not as easy to do the 3 eigenvectors at the same time. So this is good for like this computation, the local computation is good for the dominant eigenvector, because there is just one value I need to compute and I can do it. The problem is that if you try to do, let's say just for the sake of argument, let's say just the top 2 eigenvectors, how would you do it? And what is the computation that you have to do? So let's think about what you have to do if you want to do 2 eigenvectors. So let's say, the task is that you want to do spectral clustering, okay? And in the spectral clustering, so let us see that we do, ratio graph. Okay, so you have to find actually the k eigenvectors, k smallest eigenvectors, k smallest eigenvalues, and corresponding eigenvectors. Okay, so now k becomes the parameter. So this is basically depending on how many clusters you want to find in your graph. And so this requires us to compute, so let's say we start with, in this case we'll start with the Laplacian. So we'll say, okay, compute this matrix. So we compute the Laplacian matrix. And then for this Laplacian, let us say for the time being I need to find 2 clusters, so I have to compute the top 2 or the smallest 2 eigenvalues. So k equal to 2. So now what do we do? So in this case, the idea then would be that you have to orthogonalize. So the idea then is that if you have to compute 2, so you have to compute 2 vectors. So this is vector, the smallest vector un, and then in this case the vector un minus 1. You need to have 2 eigenvectors. Okay? And there are of course n nodes in my graph. So essentially I'm saying you need to compute these 2 values. Okay, for every node now there are 2 values to be computed. So that's one change conceptually, that I have to compute not just 1 value, but 2 values per node. But actually it's a little bit more complex, because the whole notion of the eigenvalues and eigenvectors is that this vector, the second vector, has to be orthogonal to the first one. So you also have to ensure that after you update things, you have to do something called orthogonalization. So you have to do orthogonal. So essentially this is what it boils down to, that you may have to do your work in 2 steps. Okay, the first step, everyone borrows information from the neighbors. They update these 2 values. Okay. Now the first one will be the dominant one, that's fine. Actually in this case it will be the smallest one, but we can, the numerically one can interchange the whole thing to get that one. Let's not worry about that part. But conceptually what you have to do is you have to first compute the first sort of vector, right? So everyone updates their value. Okay, so let's just focus on this one first. So in this sort of distributed step, everyone will look at the neighbors, will add them up, okay, and it will basically update this vector. So now you have an updated vector, let's just call it u and prime. So everyone looked at the neighbor and now all the values are given to you. And likewise this can be updated simultaneously. So both of these are updated simultaneously, so you get new values for un and un, n minus 1 prime. So, and conceptually this is happening on the graph. So using this graph, these 2 things are now updated. So this can happen in the same step. Right? Everyone is looking at the previous values, adding them up, and coming up with new ones. But now the problem is that this is not the real vector, because this vector need not be orthogonal to the first one. So then we have to do the step of what is called an orthogonalization step. And essentially what that means is that you need to project this vector onto that one. Okay, so I mean I can just tell you conceptually what you have to do to orthogonalize is to, this is coming from the geometry of the problem. So if you have two vectors, this vector is un, this vector is un minus 1. So un, the angle between them is not 90 degrees. If it just happens to be 90 degrees, you're done. But if it is not, what you have to do is you have to compute the orthogonal direction. Okay? So what you have to do is you have to compute this vector. And that vector is basically, sorry, the other way around. It will be, well, it's the same, it will be this vector. So that you get a 90-degree angle between them. Okay? So this is how you orthogonalize. You have to basically look at the difference and you do the projection, find the vector that's orthogonal to un, and this vector will be called un minus 1. So starting from any two vectors, you can do this orthogonalization process. So I won't go into the details of that, but the point is that there is an extra step. So first you update, then you have to do another distributed computation to orthogonalize, then you have to update, then you have to orthogonalize and so on. So it's not as straightforward as just doing the page rank, because now you need to compute 2 or 3 or more vectors, and this is anyway not the most efficient way of doing this. So essentially what we're saying is that these kinds of methods are generally good if only limited amount of information has to be computed at each node. Once you start doing a little bit more global thing and you depend on other values, then the paradigm sort of tends to break down. And so this is also good because this is now forcing us to think about isomorphisms, right? So when you talk about embedding and pattern mining, I want to next consider how we would do mining using things like a vertex. So remember, everything is purely local. So let's think about that problem and see what we can do. I mean, the conclusion would be that it's not a very good paradigm, but at least we need to conceptually work it out and see how you might want to do this. Okay, so remember the mental picture is still this. So these vertices are labeled, let's say A, B, A, B, A, A. Every node is assigned to some machine. So let's assume I have two machines. Okay. So if I have two machines, I'm going to call them red and blue nodes. So this is the blue node. Let's call that a blue node. That's a blue node. That's a blue node. Okay, so there are blue nodes and there are red nodes, and they correspond to the machines. Okay? So I have two of these machines.
So this orthogonalization step would be sequential or will it be distributed?
The orthogonalization is a good point, I guess. So you have to take the vector and compute the dot product. Actually, that can happen in a distributed manner because every node can simply compute the product of the two values.
Something similar to reducing.
And then you do a reduction, right? Exactly. So yeah, some parts of it are sort of looking, sequential, but there is a distributed component that you can do. Then you do a reduction, and then subtraction can also happen in parallel. So it can definitely be done in a distributed manner. Okay, so here, this is the situation. You have two machines, the red machine and the blue machine, and now you have to do graph mining. And the only thing you can do is you can look at your neighbors. That's it. So I'm going to give these nodes some IDs. So let's give them some IDs. So let's just label them 1, 2, 3, 4, 5, 6, and 7. Okay, so how should we do think like a vertex? So just think like a vertex. So essentially what you can do is, this guy can look at its neighbor and can see, what pattern it sees, right? So it's a single edge. So the first step is sort of relatively easy. The first step is we need to be able to enumerate all the single edges in the graph. But you can do this, of course, this is easy because single edges are already pretty much dependent on your neighbor. So this guy looks at that and says, okay, at this vertex, so think of from the point of view of the state or the information, at vertex 1. So vertex equal to 1 should basically look at its neighbor and it will say that this pattern is AA pattern. Okay? So it looks at the neighbor and I say I found an AA. Okay, not only that, maybe it wants to keep track of what the match was. If I really want to know the IDs, it would be ID is 1, 2. So that A is 1, vertex number 1, that A is vertex number 2. So the embedding is actually 1, 2. So that's all vertex 1 can do. There's no more edges, so that's the state at vertex 1. The state at vertex 2 would be, now this is of course happening independently, right? So both of these, all the operations are happening completely in a distributed manner in the complete system. So the blue node is doing its job on in parallel with what the red node is doing. So this guy looks at its neighbors and it basically is going to update the information. It will say AA, so there's of course 2, 1. There is AA, another is 2, 4. But it also finds an AB, and that is 2, 3. Okay, so likewise you can, like I said, so single edges are easy because they only depend on one hop away. So this is ideal for local computation. So you proceed this way, and at the end of this, you just have to do a reduce operation. Okay? So after so everyone essentially is going to, so the main computation here is look at your neighbors and extend an embedding, okay, extend the embedding, and then do a reduction. And the reduction is going to give me the global frequency of the patterns. Now there are some duplicates, so maybe that is something we can try to avoid if possible. Like for example, when you are at B, like so think of vertex number 3. So vertex number 3 will also enumerate AB, or rather it will try to do BA, 3, 2, and then B will also do another BA, which is 3, 4. But this 3, 2 and this 2, 3, right, the AB and the BA, so then we get into the notion of sort of the canonicality and those things. So those things are still valid. I mean, everything that we learned in the graph mining approach, where we talked about canonical patterns, right? So the BA is not going to be canonical because whenever you have a BA, you also have an AB, so you should never do BA. So in fact, we should probably not even count this. So because it's not a canonical, someone else will find it, right? Because every edge will be found by someone else. So that not start from BA. So you can do those kinds of pruning that based on the canonicality of the pattern that you're trying to find. But this gets pretty complex because you have to worry about the embedding, the pattern, right? Everything you have to sort of keep track from each. And so anyway, this is good. So let's say we finish this. So at the end of this, we find all the frequent. We do a reduction, and we find all the frequent edges. Okay. So then we do a reduce. And then from the reduce, we find that the set of frequent edges, so F1, is basically AB. So let's see how many times does, okay, first of all, how many times does AA happen? AA 1, 2, 3, 4, 5, 6. So I guess it's 6 including all the, automorphisms. So 6 is the number of, total number of embeddings for A. So basically 1, 2, 2, 1 is a valid, there are 2 different embeddings. 2, 4, 4, 2 is a different embedding. 4, 5, 5, 4 is a different embedding. So there are 6 of them. Then you have AB. And so the AB is 2, 3. Okay, 2, 3, 4, 3. 2, 3, 4, 3. So that's 2. Then 4, 6 is 3, and then that's 4. So I think the support is 4. If I miss something, and then you can have, of course, BB. So BB is just 2. And let's just say this is not frequent. Okay? So let's say my frequency is above 2. So anyway, these 2 are now frequent. So what should you do now at the next step? So this is the key part. So the only thing now you can do is, you can only look at the local only the local neighbors. I mean, so who are you? I mean, the direct neighbors. So this information, number one, has to be replicated at each vertex, perhaps, right? Because this is a global information. I mean, the vertex itself doesn't know anything about it, because after I've done the reduction, this information is now available that which vertices, which patterns are frequent. So this information has to be pretty much broadcast to the whole graph. Okay, because you need to know which patterns are frequent, for which I can then start doing the extensions. Okay, now there's a little bit more of it's more than this, because just knowing the pattern is of no use to me, from a local point of view, because I need to know which embeddings were there. Okay, because without the embeddings, I cannot do anything. I mean, just knowing the pattern is not enough. So actually, there's you have to do a lot more. You might say the state, state information, because every one of these, AA, for example, I mean, now I'm going to explicitly list them out. So there's 1, 2, 2, 1, 2, 4, 4, 2, and then 4, 5, 5, 4. And for the AB, it was, the embeddings were 2, 3, 2, 3, 4, 3, 4, 5, sorry, 4, 6, and 4, 7. Okay, so now think of it this way. Actually, what you have to give to the system, I mean, in the distributed system, they need to have access to the embedding. So any embedding that involves 1 should be available locally in that vertex, because then it can see, okay, this is my local stuff. I am vertex number 1. How can I extend this by looking at my neighbors? Okay, so you can do this. I mean, so it's not that it's not possible, but you have to sort of ship this embedding information across all the patterns. So basically, let's think from the point of view of vertex number 2, because that's a little more interesting. So the thing is that this embedding, this embedding, this embedding, this embedding, this embedding. So these 5 embeddings should actually be conveyed to vertex number 2. We say these are the embeddings for frequent patterns. Okay, so the thing that we found frequent. So after doing the reduction, we found these patterns to be frequent, and here are the embeddings. And you need to now take these embeddings and extend them. Okay, so the state that you have to maintain at vertex number 2 is basically, this thing is now getting crowded, but the state that you have to maintain at vertex number 2 is basically, so let's say at V number 2, first of all, you have to send them all these embeddings, 1, 2, 2, 1, 2, 4, 4, 2, and 2, 3. Okay, so these 5 embeddings, now that I know this, so let's say now all the existing embeddings, you just distribute them in the system, basically hash on, if you contain that vertex, you get that embedding. Okay, so there's a little bit more work has to be done at the end of this. You have to do the reduction, you have to find the frequent guys, and after finding, so this is basically step number 1, and step number 2 is to redistribute the embeddings, because this is not part of the graph, this is something that we computed. So this information has now to be broadcast, or basically hashed. Okay, so now hash the embeddings based on ID. So in other words, if an embedding contains vertex number 2, vertex number 2 should have that information available locally so that it can extend. Likewise, if an embedding has 3, so 3 will get, for example, 4, 3, 2, 3, and those are the only 2 things that vertex number 3 will get. So any vertex that contains that embedding, you have to ship that to that vertex. Anyway, let's proceed with number 2. So, because everyone else is doing the same thing.
Excuse me, sir.
Yeah.
In this case, number 2, 3, 6, 7, all are on one machine. If we give embedding in this way, then one machine, like in 2, 3 example only, this 2, 3 is on vertex 2 as well as on vertex 3.
Yeah.
So one embedding, same pattern on same machine number of times, means the number of nodes it has.
That's fine. Because remember, you have to think, if you start doing that, right, then you have to get a little bit more, specific to how the thing does. So you cannot make any assumptions. As far as if you're just doing a high-level programming, I just want to program a graph thing like a vertex package, giraffe, thing, then you're not allowed to control what's happening under the hood. The only way you can control what's happening under the hood is you take that code, you modify it according to your own needs, and then rerun, right? For now, we cannot make any assumptions. That's why we'll run the whole thing as if we don't know who's who. But definitely, that's a valid point that in general, if you want to optimize, then things that are on the same node and if they happen to be adjacent, then you can optimize that code. But we're not worried about that. Right now, I'm just going to do purely from a local point of view, what can I do? So this guy will say, okay, I have this embedding, 1, 2, and 2 actually happens to be the vertex that I need to. So I can only extend from 2. I cannot extend from 1 because I do not know the neighbors of 1. So I only know who my neighbors are. So what I can do is I can look at 1, 2, and I can say, okay, my neighbor is a 3 and my neighbor is a 4. So I'm going to see I can do 1, 2, 3 and 1, 2, 4. Okay, so from vertex 2's point of view, if I look at this one, this will say, in this 1 and 2, I am vertex number 2, and I can go to the graph and I say, okay, query only my neighbors. So my neighbor is a 3 and my neighbor is a 4. So it will say, I can do 1, 2, 3, and I can take that same 1, 2, and I can do 1, 2, 4. Okay, and this pattern then happens to be for A, B, and this happens to be A, and so on. So you see, basically, this is the basic idea, right? That everyone pretty much picks an embedding. He says, where am I on that vertex, right? And so actually, it's interesting to do 2, 1. What will happen for 2, 1? It will be probably, in this case, it will be isomorphic. But supposing it is 2, 1, then you pick this 2, and you say, what can I extend from this one? So you'll still get, this one, and you'll get the same, you'll get the duplicate stuff back. So this would be from this one. So these are extensions of 1, 2, these are extensions of 2, 1. So now, of course, they are duplicates. So then, but this will come from the canonicality check. Okay, so because before doing this, you don't know. You don't know whether, you basically just take blindly any embedding you get, and you say, just look which node you are in that embedding, and you just extend with your neighbors. And then after doing this, you are going to eliminate things that are not canonical. That's number 1. And then again, you're going to do a reduction, and then again, you're going to basically hash on the embedding. And this is how you proceed. But you can see the kind of problem here. The problem is there's too much communication. Right? Every time I have to communicate the entire state, all the embeddings have to be made available to that node. And this is happening external to the, so this is the sort of the state you have to maintain at each vertex. And so the platform is not really helping you with that at all. It's pretty much you're forcing this paradigm onto the platform. You're just saying, I just have vertex local information, and so the only way I can make it work is I can only ask adjacency queries, and so I have to maintain all these embeddings independently of the state. Of the initial graph. So this is the real challenge that you can do this, you can code this up, but it's extremely slow. Okay, so this is one problem with this think like a vertex. So essentially we can pretty much say that think like a vertex is not that well suited for isomorphism or graph mining or graph matching type of queries, because there's too much information and you have to communicate too many things to make this work. So this is one alternative, think like a vertex. So let's first contrast this with think like a pattern. So you say, okay, fine, you can't do this. What about the other approach that we had already talked about, which was think like a pattern? So what does that mean? So here's paradigm number 2, which is think like a pattern. So think like a pattern is pretty much similar to what I did for the. So remember, I'm doing this now in the context of a single large graph. Okay? There's only one large graph, and you have to do enumeration of the pattern. So we already said in the single large graph setting, in the think like a vertex, this is what would happen. Now let's see what would happen if I think like a pattern. So you've got to, again, a large graph, and here, now the question is that you have to think in terms of only the patterns that you're trying to count, and these patterns will be the ones that will get extended. So here, we go away from the thing like a pattern approach. So you're not going to use giraffe, you're not going to use that. Maybe I want to do this in a map reduce type of framework. Because think like a pattern on top of giraffe, on top of a graph library is hard. Because again, the problem is the only way you can do that is you can do local computation. Pattern. So think like a pattern means that you only, so this is your standard approach, that you start with the empty graph. So this is your pattern space. And then you just enumerate, AA first, AB, BB. So here you are simply saying I'm going to enumerate this space here, and every time I have a pattern, I'm going to find all the matches, right? So the key problem here becomes, given a pattern or a set of patterns, which are generated independently. Okay, you don't look at the embeddings or anything like that up front. I mean, obviously everything will be looked at when you do the reduction, but the basic task is you're given a set of candidates. Okay, these are the patterns that you want to count, and you're given a single large graph, and you just need to count them. So what we can do is we can say I can parallelize or make this computation distributed. So one thing would be pick each pattern and individually basically say, now I'm going to count this pattern in the entire graph in a completely distributed manner. So someone gives me the pattern, it's like a query that I need to basically match. And so this work can be done in a distributed manner. So again, this vertex may be labeled A, this may be labeled A, this may be B, A, B, B, or something like that. And now the thing is that this one we can try to split the work among the machines, and so that would pretty much mean, in some sense, that you are okay. So now there are two approaches actually. Now the thing gets a bit more complex. As I had mentioned, when you talk about a graph and you want to distribute this work, so there are two ways. You can either distribute the computation, or you can distribute the graph itself, right? Distributing the graph means partition the graph and assign different partitions to different machines. And so when you have a pattern, every partition can then count, what the local support is in that partition. But the problem with the partitioning is, so supposing you say I'm going to partition this network, and let's say you say, okay, here's, processor 0 gets this, processor 1 gets this. There is obviously going to be a problem with the edges that cross over. What's going to happen to those edges? Right, they're neither in one partition nor in the other. So you might say, okay, fine, I want to replicate them, right? So if an edge, basically what you can do is you can say that all these edges will be kept in both the partitions. Okay, so if there's an edge that crosses over, these two edges will be replicated in this partition, and also for these two vertices, these two edges will also be replicated in partition number 1. So this way at least I can guarantee that my first level will be correct. But actually that is not going to solve your problem, because when you go to patterns of size 2, size 3, okay, the question is, you don't know a pattern that begins here. Let's say this A, B, A, and A, B, B, and then something else later. So this can be many hops away. Okay, you don't actually know beforehand. So just keeping the one edge is not enough, because you may have to dig deeper. So assume, that you had another pattern here, and for the sake of argument, A, B, 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 okay, is a chain in this case. You will not be able to find that, because this, a pattern that's here. Now that pattern has been split into two parts, right? So there's an A, B part, right? Even if you keep this edge and you say this is replicated, so A, B, B is fine, okay? This partition knows about only one neighborhood of that. So this is how far it can look into someone else's in a partition. This guy cannot look at that B because it's not available locally here. So this is the kind of the challenge you have, that you really have to, you cannot do this in a completely partitioned way without exchanging information. So the only way this can be made possible is that at some point you have to send you have to sort of maintain the frontier. Okay, I'm going to come back to this point later if I have time. You have to maintain a frontier, and you have to say that if you do find A, B, B as a frequent pattern, then this guy and the neighbors of this node should also be incorporated into that partition. So every time you extend something, you have to possibly get new neighbors and bring them into your own local partition. So you have to keep on extending the neighborhood. So this is called the one-hop neighborhood. So at the very least, you need to have this one-hop neighborhood to begin with, and then you have to possibly expand that to this, two-hop neighbors, three-hop neighbors. So every time you extend the pattern, you keep on extending your neighborhood. But then the drawback is that essentially you end up replicating the whole graph. I mean, in the worst case. Okay, ideally, maybe you can prune some things, but eventually what might happen is that P0 gets to look at all of P1, and P1 gets to look at all of P0. So essentially, you replicated the whole graph, So that's why distributed graph mining is extremely challenging. Okay, when you actually implement this, it's not at all an easy task. And in fact, many systems are not really tackling this problem to begin with. So what they assume is that the data has been partitioned in some way, but they will give you any query. They'll satisfy any query. So if I ask for the neighbors of this, it will give you the neighbors from the distributed file system. So in a way, the idea that I told you about caching, right? It's on demand. Okay, so the extension happens pretty much on demand. That is, at some point in time, you have a pattern and you look at the embeddings, and you need to know who the neighbors are. You basically query the system. You don't worry about where that edge is. You don't worry about whether it's in P0, P1, whatever. The system has taken the graph. The system has split it in some way. You simply ask the system, who the neighbors are, and it will just return you the answer. But when it returns you the answer, you can cache it locally. So that's as if you're replicating this edge in that partition. So all existing systems basically do this. Okay, they do not explicitly partition the graph in this way. They just partition it in some manner, and they just ensure that all adjacency queries can be answered accurately. The system will take care of it. So for our purposes, then we don't have to worry about this explicitly partitioned network. We can just say our conceptual view is that I can pretty much ask any query from anyone. So essentially, in a way, you're saying that the whole graph can be seen from any node. Okay? And when I say it can be seen, on the disk it may be partitioned, but I can query anything. And when I query, it will just bring those neighbors into my cache. So that's where all the existing frameworks basically implement this idea, that you're allowed to query the neighbors of any node in the network, regardless of where it is. So it may not be, again, the most efficient way, but at least it will be correct. You can guarantee correctness of your method. Okay, so with this sort of preview, now I need to count AA. So what should we do? So now the thing is that, okay, the entire graph is available to us. So I think the logical solution would be, there are two ways. I can say AA needs to be counted, and I have 10 machines. So then I need to basically assign that job to 10 different machines. That's one approach. Or I can say I've got these 3 patterns, and actually eventually I'll have many patterns. So I can give one pattern to one machine. Okay, so that machine's sole job would be to look at the entire network and simply count all the embeddings. So this is basically whether you do sort of partitioning or, so this guy is potentially going to have some embeddings. So one idea is that what you conceptually want to do is let one process, find these embeddings, another process find these embeddings, another do this. Or the simpler idea is that take your pattern set and, basically say that this whole thing will be done by process 0, this whole thing will be done by process 1, this will be done by machine number 3, and so on. Just distribute in a round robin manner, and they can go and compute. And this is simpler to implement because I can take that pattern, I can say this pattern, you are responsible for it. So the machine basically goes through the entire graph. You can check whenever there's an AA, increments the count. Another AA found, no, there's no count. So AB, some other machine gets it. So now you see the load imbalance problem, right? So AA, there's only one occurrence of AA in this whole network. And so machine 0 will just find that, let's just sit idle. Whereas machine number C1 will take AB and it have many instances of AB. So it will do this AB, that AB, that AB, that AB, and this AB. So there's a lot of work for AB. So machine number 1 will be busy, doing some work, and machine number 3 will also be, free. I mean, BB, there's 1, there's 2, there's 3, a little bit more, but there is a sort of skew in the computer. But we can't do much. I mean, there is skew. This is the easy way to program it. But the good thing here is that one machine has done all the work. That means it can do the reduction automatically. It knows the global support. So every time you finish this, I know exactly whether or not a pattern is frequent or not. And then I get my new set of extensions. So I can take AA. In this case, let's say AA is not frequent. This guy will be frequent. So I do this. I compute the support. And then I broadcast this information among all the machines. This is my new, global set of patterns. And now we can do extend this. So I can extend this pattern by one more.
So is this problem like that random graph generation problem when we are finding patterns and adding edges?
In what sense? So when you say like the random graph?
Because, for example, we have a pattern AA. So next time we have to query its neighbors and find another pattern.
Yeah.
So there are possibilities of multiple edges there, multiple neighbors there, and so in that sense.
But here we are looking at pretty much the embeddings, right? So in the sense that we are not doing any randomization.
And the embeddings are available.
Yeah. So well, you can maintain them, but you don't need them. Okay. So the thing is that.
Do we need to extract the embeddings first and then just start querying, or we have the embedding database and then?
Yeah. So that's actually a good alternative. So what you can do is that. So let's I think that's a good point. So if you look at AB. I just computed AB and I found that AB is frequent, and I of course have all the embeddings of AB, right? Okay, now from this AB, I'm going to generate possibly new candidates. I can say, remember the rightmost extension, there are two ways of doing it. So there's AB here, and in this case there are going to be 4 possible extensions, right? So there's going to be ABA, ABB, and then you're going to have ABA and ABB. Okay, so AAB, this is ABB, ABA, BAB. So they're all distinct. So these would be the 4 extensions, right? Possible. Just you extend and you say this is what you have to count. Okay? And now, of course, you could use these embeddings. You could say I can go back to this list, but there are several issues. Now, this list, are you going to broadcast this to all the machines? Okay, or because now there are 4 extensions, they might get go to different machines. So there is always this communication versus computation trade-off. You could say that I'm not going to communicate anything because maybe communication is expensive, and I have to communicate very large amount of information. So what I'll do is I will actually let them recompute everything on their own. Okay, this will get assigned to some machine, this will get assigned to some machine. They will refine all the embeddings that are in the graph. So which is better is not clear. It depends on the graph, it depends on the data characteristics. So ideally you should have a hybrid approach. Initially the embeddings will be large, when you do size 2, size 3, and at some point they become small. So when they are large you should not communicate them. When they become small you can communicate, and that will be faster. So these are again sort of decisions being made from algorithmic point of view. But so basically you get the picture that essentially I have an expanding tree, and basically you keep on reassigning every pattern. So one node, one machine gets one pattern, it can count in that graph. And if you want to do more fine grained, you assign multiple nodes to compute the embeddings for this one. You can also do that. So if there's not enough work, people can be kept busy by splitting the work. So that means instead of, like I said here, instead of computing, just one node doing the whole thing, you split it up into chunks and say, you find in this chunk, you find in this chunk, and you can go that way. But the problem here is high load imbalance. Okay, so things like a pattern is not very efficient.
So finding these embeddings will also be computationally very intensive.
It is computationally.
It depends on the application.
Absolutely. Yeah. So graph mining is challenging. It is actually, yeah. So that's why pattern matching, pattern discovery is very costly. I mean, you're doing graph isomorphism. At the end of the day, if your graph is very sparse and the labels are not too highly connected, this can happen very quickly. But if you have very dense structures, lots of similar labels, then you're basically stuck in all kinds of automorphisms. Okay, so let's take a break here. After the break, I'm going to talk about the embedding, and we'll talk a little bit about the exam tomorrow. I know some people have questions.